In this lesson, we will learn about polynomials and operations with polynomials. Before we begin working on operations with polynomials, let's talk about some of the vocabulary associated with polynomials. In algebra, a term is either a single number, variable, or numbers and variables multiplied together. In this problem, we have three terms, 3x squared, 2xy, and 25. A grouping of terms separated by addition, subtraction, or division is called an expression. Here we have an expression 3x squared plus 2xy. We also have this written into an equation because we have an equal sign and numbers on either side. Like terms are terms that have the same variable to the same exponent. The coefficients do not need to match, just the base of the exponent and the exponent itself. Listed on this page, we have four different terms, 3x squared, 2x squared y, 3x, and 7x squared. But out of these four terms, only two of them are like terms, and that is 3x squared and 7x squared. They're like terms because they both have an x to the second power in them, and only an x to the second power in them. This term has a y in there with the x to the second, so that is not a like term with 3x squared and 7x squared. And 3x has an x by itself, but it does not have an exponent of 2, so it's not the same variable to the same exponent. The two like terms are 3x squared and 7x squared, and we would be able to combine those together in an addition problem. A polynomial is an expression containing one or more terms consisting of variables and coefficients that involves only the operations of addition, subtraction, multiplication, and non-negative integer exponentiation of variables. Below we have a pretty typical polynomial. It has three terms in it, so this specifically would be called a trinomial. The terms are 3x to the third plus 2xy minus 4y squared. I can't combine any of these because none of them are like terms, so all three of these terms are individual terms in our polynomial. So what exactly makes up a polynomial? Well, 2x is a polynomial, x minus 6 is a polynomial, negative 3y squared minus 4/9 x is a polynomial. Then the next one, which is a whole bunch of numbers, 2xyz plus 3xy squared z minus 0.4xy minus 150y plus 0.9, that is a polynomial. Remember, these need to be just addition, subtraction, multiplication, and in whole number exponentiation, and that is the case for all of those on the left box. 256x squared, that has a whole number exponent plus addition, 77x to the third, whole number exponent. Even the number 7 by itself could be considered a polynomial, even though it's just a constant term. What are not polynomials? 2x to the negative 2 power, that is not a whole number exponent, that is a negative exponent. It's not a positive integer exponent, so that is not a polynomial, not with that negative exponent. The square root of y, the square root is actually a fractional exponent, so not a whole number exponent. That is y to the 1/2 power. So that is not a polynomial. 2 over x plus 2, you have division, and division's okay. We have 4/9 in the other side that is a polynomial, but you can't have a variable in the denominator and call it a polynomial. And 1 over x, same rule. Can't have a variable in the denominator. That's not a polynomial. So polynomial is a catch-all term, meaning that has one or more terms in it. These are specific to the number of terms. If you have one term, your expression is considered a monomial. If you have two terms, your expression is considered a binomial. And if you have three terms, your expression is considered a trinomial. Notice none of these can be reduced any further than they already are. There are no like terms in any of them, so they are reduced to their simplest possible number of terms. Now, the degree of a polynomial can be a tricky topic, but for the purpose of this course, we're only going to consider degrees of polynomials that only have one variable in the polynomial. If if a polynomial expression has one variable, in all of my examples, that variable is x or nothing, the degree is the largest exponent of that variable. So in 3x to the third minus 2x squared plus 4, the degree is the largest exponent, which is 3. In x squared minus 2x minus 3, the degree is 2. And 2x minus 1, the degree is 1 because there is an exponent to that variable, and that exponent is 1. And for just a constant term, like 4, the degree is 0. Now, when you have a degree of 3, you are considered to have a cubic function. When your degree is 2, you have a quadratic function. When your degree is 1, or there is no exponent other than just the 1, you have a linear function. And if there's no variable whatsoever, you have a constant function. All of those names will be very important when we start graphing these. The final thing we're going to look at before we start adding, subtracting, and multiplying polynomials is the concept of standard form. Standard form means writing the terms of the polynomial with the highest degree first, and then continuing down until you get to any constant term last. So we are going to put this polynomial into standard form. So 2x squared plus 3x to the third minus 4 plus 4x. Well, I notice that my highest degree is this 3x to the third. So I'm going to write that first. And it's a positive number, so I just keep it positive in front. The next highest degree is 2x squared. So, and that's also a positive number, so plus 2x squared. Then my third highest is 4x. That's a linear term, so plus 4x. And then finally, I have minus 4. That's a negative number, so I'm going to make sure I put a minus sign in front of it and then a 4. So that is me rewriting that polynomial in standard form. Now, typically, if we were going to factor this, or if we were going to multiply it, we would kind of want it in standard form. It makes it easier to simplify, and it makes it easier to collect like terms when everything is written in standard form. So here we are. We are going to add two polynomials together. And when you're adding two polynomials together, essentially what you're doing is collecting like terms. So first I'm going to take a look at my polynomials and make sure that everything's in standard form. We'll just make it a little easier. So 2x to the third minus 5x squared plus 3x minus 9, that is in standard form. We have our highest degree first, and then our next highest, and then our next highest, all the way down to our constant term, minus 9. Let's look at the second polynomial. X to the third plus 6x squared plus 11. That is also in standard form. Notice there's no x term. There's no like linear x term, x to the first power, and that's okay. Now, in order to add these two together, we can drop the parentheses because there's no more simplification that can be done inside the parentheses. And we can just simply add all the like terms together. So 2x to the third is a like term with x to the third. So I can add those together. 2x to the third plus x to the third. We add the coefficient, becomes 3x to the third. Then we have negative 5x squared. And that is a like term with positive 6x squared. Now, one's a positive number, one's a negative number, so we'll subtract those. 6x squared is bigger. 6 minus 5 is 1, so that will just be plus x squared. Now we have our 3x term, and that does not have any like terms, so it just copies over. It's a positive 3x, so I'll write it that way. And then finally, we have minus 9 and plus 11. Well, 11 minus 9 is 2, so our solution will have plus 2 in it. So adding these two polynomials together, combining like terms, that is, we get 3x to the third plus x squared plus 3x plus 2, and that is written in standard form. And so we're done with it. Here we have another two polynomials, and each of them is written in standard form. There's no more simplification I can do in any of these. 3y to the third minus 2y squared minus 7y. There's no like terms there. I can't combine those together, so I can eliminate the parentheses. And on the other side, negative 4y squared, 2y, and minus 5. No like terms there either. I can't combine those anymore. I can just eliminate these parentheses. Okay, so now we go back to combining like terms. So 3y to the third, there are no other like terms. There's no y to the thirds anywhere else in this problem. That will carry over into our answer. And then we have negative 2y squared and negative 4y squared. So I'm going to add those two together. That will give me negative 6y squared, or minus 6y squared. Next like terms are our y terms, negative 7y and positive 2y. Those will combine together to give us a negative 5y. Remember, when you're adding these, you're just changing the coefficient. You're not changing the variable or its exponent. And finally, we have a minus 5 over here. That has no other like terms. I copy that over to my solution. It becomes minus 5. Now my entire problem is written in standard form, and my solution is written in standard form as well. So we have accurately added the two polynomials together. Subtracting polynomials is essentially combining like terms like adding polynomials is, but there's one major step that you need to do before you start combining like terms, and many students have difficulty with this until they realize that you just do it at the beginning and then combine like terms and everything else will be fine. And that is, we don't actually want to subtract polynomials. We want to add them. So I am going to distribute that negative minus sign in between the two polynomials to everything in the second polynomial. So I'm going to change that to a plus and then change everything, the sign of every number in the second half. I'm going to take all my positive numbers and make them negative, and all my negative numbers and make them positive. So I made that minus sign a plus, so my positive 8x to the third is now a negative 8x to the third. My negative x squared is now a positive x squared. My negative 5x is now a positive 5x, and my positive 1 is now a negative 1. You have to distribute that negative to each and every term in the second polynomial, not just the first one. That's why those parentheses are there in the first place. So you distribute that negative sign to everything. Okay, now that I'm done distributing that, now that I have a plus sign in between the two, now I can finally drop off all of the parentheses and start combining like terms together. So first, 3x to the third, I can combine that with negative 8x to the third, and that becomes negative 5x to the third. My 2x squared is positive, and my x squared is also positive, so that's 2x squared plus 1x squared is 3x squared. I have a negative x on this side and a positive 5x on this side. I can combine those together. 5x minus x is 4x, so plus 4x. And then my constant terms, I have a 7 in the first polynomial and a negative 1. 7 minus 1 is 6. I will say plus 6. And I successfully subtracted these two polynomials. Another set of polynomials. Everything is written in standard form, so I don't have to worry about manipulating anything like that. But there is the minus sign in between, and we do not want to actually subtract these polynomials. We want to add them. So I'm going to change that sign to a plus and then distribute the negative to every term after it. That becomes negative. That becomes negative. This already was negative, so it becomes positive. So now we have an addition problem between two polynomials. So let's combine like terms. 5z squared and negative 4z squared. We're going to subtract those because one's positive and one's negative. And we get z squared. And then negative 9z, that doesn't have any like terms, so I'm just going to write it as a minus 9z. You could also write it as a plus negative 9z. It's really your choice. And the last step is a positive 3 and a positive 12. 12 plus 3 is 15, so plus 15. Multiplying polynomials. Now, to multiply two polynomials, you multiply each term in the first polynomial by each term in the second polynomial. Everything gets multiplied by everything. And there are so many different methods for helping this. There's a lattice method. There's, if you have two binomials, you can FOIL it. But what I'm going to show you today will work no matter what size any of your polynomials are. Those other methods work great, and if you really like using them, by all means, continue to use them. But the method I'm going to show you today is just repeated distribution, and it will work regardless of what size your first polynomial or your second polynomial are. So here we go. So we are going to multiply 2x times 3x minus 4. And many of you have seen this before, and you notice that you are going to have to use the distributive property. So one multiplication, one term times a binomial inside of parentheses, you multiply that by each of the terms. So 2x times 3x, well, the 2 times 3 is 6, and x times x is actually x squared, minus 4 times 2, which is 8, and x times 1 is just x. So 2x times 3x minus 4 will be 6x squared minus 8x. And here you can see I wrote it out just a little bit neater, kind of showing what I was multiplying out. We're still multiplying 2x times 3x, that's what I wrote here, and then 2x times the negative 4, 2x times negative 4, and I ended up with 6x squared minus 8x. All right, in this problem, now some of you might have learned about foiling before, and that works totally fine and will work in this case. However, I'm going to show you how another way to look at this is just repeated distribution. So I take each of the terms in the first polynomial. So negative 2y squared, and I'm just going to change this minus sign to a plus negative. It's easier to distribute that way. And then I'm going to multiply negative 6, each of those terms, by the entire y minus 2. So let's see how you would write this. So negative 2y squared, right out of the first part of the first polynomial, multiplied by the entire quantity y minus 2. And then I changed that minus sign to a plus just for this reason, watch. Plus negative 6 times the entire quantity y minus 2. Now by doing it this way, I'm multiplying each of the first terms by the entire second term. So I know I'm multiplying everything in the first term by everything in the second term. Now, it became two different distribution problems. So I have to distribute negative 2y squared to the y and the negative 2. And I will also distribute the negative 6 to the y and the negative 2. So let's multiply those out. Negative 2y squared times y is negative 2y to the third. Negative 2y squared times negative 2, well, negative times the negative is a positive. 2 times 2 is 4. 4y squared. Then we have negative 6 times y, so plus negative 6y, and I changed that minus sign to a plus negative just for this reason. Now I'm going to multiply negative 6 times negative 2, and if you didn't change that to a plus negative, you might not know that it's a negative times a negative there, but that will be plus 12. So just make sure that in this middle part right here, you change it to a plus negative, otherwise your signs might get messed up as you're doing your distribution. Now I'm looking at this problem, and normally at this point we'd have to collect like terms, but in this particular problem we have no like terms. We have negative 2y to the third plus 4y squared plus negative 6y plus 12. No like terms. I could rewrite it and put that minus sign back in front of the 6y, but I could just leave it exactly like that, and that is a totally acceptable answer. It's written in standard form. My highest degree is first, and everything has been multiplied by everything else. So great job, everyone. Let's try another one. Oh, before we get to that, this is the same thing kind of written out more slowly. A little bit neater. Just remember, we're repeatedly distributing this. And remember, if there's a minus sign here, make it a plus negative. Just makes the distribution so much easier, and it ensures that you're going to get accurate answers. Excellent. This will be the last one we practice. Now we have a trinomial in front times a binomial second. And I'm still going to set it up exactly the same way. I'm going to take this minus side here and make it a plus negative. But other than that, I'm going to take each of the terms in my first trinomial and multiply each of those terms by x plus 3. So 3x squared times x plus 3 plus negative 2x times x plus 3 plus 4 times x plus 3. And it might seem like a lot of writing, but it really ensures that you multiply everything in the first polynomial by everything in the second polynomial. So some distribution here. 3x squared times x is 3x to the third. 3x squared times 3 plus 9x squared plus negative 2x times x is negative 2x squared. Negative 2x plus 3 is plus negative 6x. 4 times x is plus 4x. And, I forgot my arrows. 4 times 3 is 12. I forgot these ones. Okay, I have some like terms here. And if you set up your problem in standard form, your like terms end up right next to each other. Like x squared and 2x, those are like terms, and negative 6x and 4x, those are like terms. So I can combine those together, just like we did with adding and subtracting polynomials, and simplify this a little bit further. So the 3x squared will stay, that is no like terms. 9x squared minus 2x squared is plus 7x squared. Then negative 6x plus 4x is minus 2x, or plus negative 2x, either way. And then the 12 had no like terms, so plus 12. And even now, my answer is in standard form, and it's completely acceptable. 3x to the third plus 7x squared minus 2x plus 12. Let's see it typed out a little bit neater. There it is. I'm just going to write in some plus negatives here. You'll notice that I did distribute negative 2x to each of these terms because they both ended up negative in the next step. And we'll continue to do it over here. All right, same answer, both pages. Okay, I think we're ready to try some of these.